Right, so today I'm just going to briefly go over this concept of guesstimation, which is this kind of useful way of using kind of maths kind of in a kind of a rough and ready way that will kind of help you kind of solve problems or answer questions or help you understand a system. Okay, so basically you work for a problem and get a number that's approximately the right number, but it's quite easy to get rather than actually doing all the maths in your head yourself. So it's kind of really championed by this guy up here, Fermi, who was a physicist. And it's basically useful for, if you've got a very complex sum with lots of kind of big or numbers in that have got many, many digits in or something like that would make the calculation difficult, you can just estimate what they would be, make the calculation a lot simpler, okay, and see if you come up with approximately the right answer, okay, or something that's physically plausible. Okay, so you're not trying to get the right number, okay, you're just trying to get a number to within an order of magnitude, so that's kind of plus or minus like a factor of 10. So if the answer was 30, getting an answer of 10 or 100 would kind of be okay. And always show you're working when you're going through these, because if you then end up with something that's looking a bit odd, then that helps you then go back and find out where you might have gone wrong. So we'll just go through an example of that. So we might come up with a problem where you need to know what the mass of the atmosphere is. So if we're kind of pumping out maybe some kind of chemical into the atmosphere, it could be CO2 for instance, and we knew how much we were putting out, and we wanted to know how much that changed the concentration, we need to know how much of the atmosphere there was to dilute our gas into. Okay, so it's kind of useful number. So it was quite hard to actually weigh the atmosphere. You kind of like think about, well, how much kind of atmosphere can I get on a scales, or if you try to kind of like divide up the atmosphere into little boxes, because different parts of the atmosphere have different amounts of stuff in them. So the atmosphere at the bottom of the atmosphere near the ground is much denser than the atmosphere at the top. Okay, so it's quite hard to get any one bit of the atmosphere and make that representative. But we can make use of some physics to kind of like cheat our way around the system. Okay? So one thing we know is that atmospheric pressure, okay, is approximately 1,000 millibars. Okay? And that in SI units is 10 to the power 5, so 100,000 newtons per meter squared. So every kind of square meter of ground, there's 10 to the 5 newtons pushing down on that. Okay. So that's a measurement that's actually very easy to make, atmospheric pressure. You basically just make a vacuum and work out how much is being pushed in on that vacuum. We know that 1 newton is 1 kilogram per meters per second squared. Okay, that's because newtons is force. Okay, so Newton is a force, and force is equal to mass times acceleration. So the force applied by the atmosphere is to the ground is just due to its mass and it being accelerated. Okay? And the acceleration is gravity pulling down on the atmosphere towards the centre of the Earth. So we know what acceleration is. That's just little g, okay, which is 9.81 meters per second squared. Okay? Now, just with this information, we can work out the total weight of the atmosphere. We're going to have to make some assumptions as well. We also need to know how big the Earth is. So I'm just going to go through how we would do that. So we say atmospheric pressure is 100,000 newtons per meter squared. And the mass of the atmosphere, okay, is the pressure times the area of the Earth's surface. Okay, so if we know how much each meter squared weighs, we just need to multiply that up over the whole atmosphere. Okay, that should actually be mass times area. So to work out that mass, okay, so we just need to rearrange this equation. Okay, so we've got F equals m, in this case now g. So to work out the mass, okay, we divide both sides of this equation by g. Okay, so if you always do the same thing to both sides of the equation, and now m times g divided by g is the same as m times g over g, which is the same as m times 1, which is the same as m. So we know that those can all go away. These can all go away. Go away, go away, go away. Oh, that's awful. Guess that's why they don't like people bringing their own pens. So we've got this equation. Mass is just force divided by gravity. Okay? So we can now make our first kind of approximation. And so instead of saying gravity is 9.81, because dividing 10 to the 5 divided by 9.81, that's not a number that you can instantly do in your head. Okay? But if I make this 10, okay, approximately 10, 9.81, certainly to the nearest, to one significant figure, it's 10. So we'll go back, and now we've got our mass is equal to the force, which is 10 to the 5, divided by 10. Okay? And now we're working in these powers of 10. That makes this much, much easier, because that's just 10 divided by 10 to the 1. So we then just minus 1 from 5. That gives us 10 to the 4. Okay? Which is the answer that is written down there. So that's the mass. For every 1 metre squared, there's 10,000 kilograms of atmosphere above it. Okay? So that's 10 tons of atmosphere above. If I was standing on a square metre, there'd be 10 tons of atmosphere above. All the way to the top of the atmosphere. So all we need to do now is multiply that by the area of the Earth. Okay, now we can, we should know that the surface area of the sphere is 4 times pi times r squared. So we can make some more approximations here now. Okay, so we can say 4, we can approximate 4 to 4, right? That's pretty standard stuff, yeah? Pi, 3.14159. That's not very kind of nice to deal with, so we'll times 3, call pi 3, should we? Times the radius squared. Okay? Now, anybody radius of the Earth? 6.2 something, yeah, 6 times will be times 6.23 something times 10 to the what? It's not 6 meters, is it, or 6 feet? What's the unit you're thinking of? Yeah, so it's 10 to the 3, so it's 6,000 kilometers. Okay, but all of our other units are in SI units, meters per second. Okay, so if we convert it now, yeah, so that's kilometers. So if we convert it now, before we do any powers of squaring, all this kind of shenanigans, we just times it by 10 to the 3. Okay, to get the number of meters. So that's, and we'll get rid of all of that stuff there. We just call it 6. So that then, I'm covered in stuff now, aren't I? 6 times 10 to the 6. Happy campers? Now, importantly, all of that is squared. Okay? That's the surface area. So A equals that. So the mass of the atmosphere is going to be this number, yeah, times whatever this is. Okay, so we'll have mass of the atmosphere equals 10 to the 4 times 4 times 3 times 6 times 10 to the 6 all squared. Okay, so that's now slightly simpler, and we can carry on simplifying. Okay, so 6 squared, 6 times 6, 36. I mean, even if you didn't know, it's about 40, somewhere between 50 and 10, right? We'll call it 36 for now, shall we? 36 times 10 to the 6 squared.
10 to the 12?
Yeah, so because it's in a bracket and it's raised the power, you're raising a power to a power, so you just times them together, times 10 to the 12. Okay, 4 times 3?
12.
Yeah, to 12's hard, yeah, let's just call that 10, shall we? And actually we've made this one, let's just make this 40, right? Because, you know, made that a bit smaller, made that a bit bigger. Nice round numbers, we like round numbers. Times 10 to the 4. Okay? Now we can simplify things. I mean, we've got now 10 to the 1, 10 to the 4, 10 to the 12 times 40. Okay? So 40s can be written 4 times 10 to the 1. Yeah? Then we've just got some things to times together. So 10 to the 4 times 10 to the 1 times 10 to the 1 times 10 to the 12. So the answer is 4 times 10 to the 12, 13, 14, 18. Yeah? Kilograms. Okay? And that would be our answer. So you really a bunch of guesstimations to come to an answer that's about right. Now in this case, we can't really check whether that's right. Okay? It'd be quite difficult to check that's right because you have to know what the atmosphere weighed. But in quite a lot of cases, so for instance, if we were working through and working out the radius of the Earth or something that we know kind of inherently what's like about right, if we came up with an answer that was 1,000,000 kilometres for the radius of the Earth, we might think that's the wrong answer. Okay? How have I got that so wrong? Oh no, that's the area of the Earth. Yeah. Boom! Yes! I thought I was, yeah. So 4 times 10 to the 18. It's not like I read through the lecture just before. Anyway. Okay, so that's guesstimation, and that's really useful when you're kind of like working through problems just to see if you're getting approximately the right answer. So for the rest of the lecture, we're going to start working on algebra and manipulating equations. So this is quite an important part of the reason we do this course, because when maths is used in other courses, okay, so quite a lot of the thing we're asking you to do is just simply manipulate an equation to get from one equation to some other equation where you've got the variable you want to know, okay? So this is quite important. So it's just basically learning a whole bunch of rules, which is a bit tedious, but such is life. So the first kind of rule is that if you've got two fractions times each other, okay? So in this case, at the top, A over B times C over D, that's the same as putting basically a line, continuing that line all the way through, and the times top and bottom. Okay? So you see those two expressions at the top, they are the same. Okay, so we could kind of look through this one here. So this one, we've got 2/3 times a ninth. Okay, so that's the same as 2 times 1 divided by 3 times 9. So that would be 2/27. Yeah. Just like this one here, 4 times x over, 4/5 of x over y is the same as 4x divided by 5y. Very straightforward. I'm not going to get you guys to go through this on top hat because that's quite straightforward. Happy that that's quite straightforward? Okay. I mean, they're probably on the test, so the tutorial thing. So. Okay, so when you're doing division, exactly the same rule, except you turn the second fraction upside down. Okay, so in this case, the top one, it becomes AD times BC. Okay, so over here, this would be 4 times 12 divided by 9 times 1, so 48 ninths. Okay, whatever fraction that happens to be. Okay, and this one would be, okay, what's the answer to this one? What's this? Sneaky, aren't we? Okay, so you can work through these in your own time. They're fairly standard. So those are the rules for when you've got division and multiplication of fractions. Now, if any of those things have got a plus or a minus in them, the rules kind of don't work. So before you do any of these things, check that there's not an addition or subtraction in there. Okay? So the next thing we're going to talk about are these. Oh, no, my little doggy's fallen down. Essential life skill being able to do that. Are these brackets. Okay? And being able to deal with these brackets, to basically to take them away, and crucially to be able to put them back in an equation, okay, is really quite useful. And sometimes it's not the hardest part about manipulating equations in these brackets is that you can add them and take them away almost kind of like willy-nilly, right? Whenever you want to. But knowing when is appropriate to group things together within a bracket and then kind of take that out of part of the equation. So first of all, we're dealing with if you've got brackets and you want to remove them, okay? The rules are basically anything that's times by a bracket, so this is A times the whole bracket. You basically take out each thing within the bracket that's got a kind of like an addition or subtraction between it and do the multiplication on that separately. Okay, and it's important to consider that if you've got a minus like this, that minus is kind of bound on to, or is related just to that C there. So you first of all do the first one's at A times B, and then plus C times A, or A times C, whatever, same thing. With the bottom one, it's kind of I kind of like to think of it. Let's just write that bottom one out. A, blue is quite nice, isn't it? B minus C. Okay, you can write that out slightly differently as A is B plus minus C. Okay, those are the same. Okay, if you're adding a negative, that's the same as just a negative. Okay, so in this case we would be doing A times B plus A times minus C. Okay, so A times B, which is AB. Okay, plus A times minus C, which would be minus AC. Okay? Sometimes it helps to explicitly separate out the minuses. Okay, but you have to, anything times a bracket, it's times each part of the sum or negativeness in the bracket. These are some boxes which help show that are not necessary. Okay? So some examples of us removing these brackets. Okay, so if we were to, in this case, 2 times 3 plus 2. Okay, so we could see how that's 2 times 3 plus 2. Okay, so if we ignore the fact that these are numbers to start off with. Okay, so that's 2 times 3, which is 6, plus your man there. 4. Yeah. Okay. So that's 10. Yeah? Happy, 6 plus 4 is 10. So that's the same as if we'd have evaluated this bracket first. So 3 plus 2, 5, times 2 is also equal to 10. Okay? So that's how the magic works. So slightly harder ones. Let's not do that one. Let's think about doing this bottom one here. So if I set you a task. So I'm going to want a word answer. Okay. So in this case, I want you to enter the answer as if it were an Excel formula on Top Hat, if you're into that kind of thing. If you're not, then you can write on the forehead of the person next to you. So think about 3x times x plus 2 and then minus 7x squared. Okay. So the first thing to do is deal with the bracket and then see if there's anything that simplifies. Ooh, one person. Someone super speedy. Oh, 2 people. People still tapping stuff away. Okay, so for those that have working way through the stuff, so the first thing to do is to times the first part of the bracket, so 3x times x. Okay, so that will be 3x squared. Okay, and then times the second part, 3x times 2, just 6x. So plus 6x, and then minus 7x squared. Okay, so that's removed the bracket, but we can still simplify it a little bit further because we've got two terms that have got x squared in. Okay, so 3x squared minus 7x squared is minus 4x squared. So we can simplify this a little bit further to 6x minus 4x squared. Okay, you could equally have written that down minus 4x squared plus 6x. Those are the same. Okay, so you don't have to just be a single variable that's the thing that's times the bracket. It can be a bracket itself. So instead of just being kind of x times c plus d, you can have a plus b times c plus d. So two brackets times each other. And in this case, you basically, it doesn't matter which way around you do it, you take one of those things in a bracket, you split it in half and do the multiplication on that, and then you do the same with the other half of it. So in this case, we're splitting apart c plus d, and we're doing c times a plus b plus d times a plus b. D, a plus b. Yeah, you see how you're splitting apart one of the brackets and then doing the expanding of the brackets separately. Okay, so that then you expand those individual brackets. Okay, AC, BC, and then that gives you this longer form here. Okay, and you can see that none of those are the same in this case, so there are no things that you can simplify. Okay, similarly, if you've got a minus, when you split apart the bracket there, okay, put the minus in the middle, and then do your expanding things out. Okay, so let's just go through a few examples of those. So let's take the top one. Look at that. So you've got a thing in a bracket times a thing in a bracket, and that thing is x plus 1, and the other one is x plus 3. Okay. So the first thing we do, we're going to split one of those things in half. Okay, let's split this first one in half. So we've then got x times x plus 3. I'm always in the way here. And then plus 1 times x plus 3. Yeah, happy campus? Okay, then you just do the expanding the brackets for each one individually. So x times x is x squared plus 3x. Okay, that's that bracket. And then plus, and then we've got 1 times x is x, and then 1 times 3 is 3. Pretty happy with that. We can simplify this because 3x plus another x is just 4x. So then that becomes x squared plus 4x plus 3. Okay? So we've taken a slightly more complicated example here with two brackets and expanded those out to get an equation that's easier to solve. And we'll come on to solving these equations in future lectures, which will be fun. Okay, so let's just make sure that you guys are kind of up to speed on that, and let's do let's do this one. This is the hardest one. Okay, so this is minus 2a plus 3b times a plus b. So let's get working on that one. I'll open up a word answer. There you go. So we'll see how that pans out, and I'll see if I can do it, because in black, like that. Okay, so I think most people are getting on there. So so to point out that this minus at the front, okay, that's the same as saying minus 1 times that bracket times that bracket. Okay, so then you've got three things. You've got a minus 1 times a bracket, and it doesn't matter when you deal with that minus 1. You can deal with it at the beginning, or you can deal with it at the end. So you can times everything by minus 1 now, or at the end, or you can times half of it by minus 1 and then follow that through later on. Okay, you just have to remember to deal with it. Okay, so let's deal with it at the beginning. So we could just times all of this stuff by minus 1. So it's the same as let's go. So minus 1 times 2a is minus 2a. Okay, plus minus 1 times 3b, which is minus 3b. And you see there, by me putting the plus in, okay, and then timesing minus 1 by 3, I've now got a plus minus 3b. Okay, so that's the same as, yeah. Okay, so I've dealt with that minus now, so now it's the same as a plus b. Okay, so I need to multiply this out. Okay, and I'm going to split it, this one first, that's going to be 2 minus 2a times a plus b, and then minus 3b times a plus b. Yep, that's why. Yep, that's what it said. So then we multiply this one out. Minus 2a times a minus 2a squared plus minus 2a times b, so that would be plus minus 2ab. Okay, so that's a plus or minus, we can get rid of that plus now. Then we've got minus 3b times a, minus 3ba. Okay, and minus 3, so plus minus 3b squared. That makes some sense. It's confusion.
No, I've got this in answer, but you just did it in a different way.
Yes, no, that's absolutely true. I'm doing it in a different way. You can do it in. There are lots of different ways you can do it. Okay, but as long as you follow the rules, okay, it doesn't matter which one you do first, you'll end up with something that's kind of right. Now, we can simplify this a little bit because 2ab is the same as, well, so something times ab is the same as something times b. So it doesn't matter which way around these are multiplied. Okay, so this could be written minus 3ab. That's the same. Okay, so now we've got minus 2ab and minus 3ab, so we can combine those together to get minus 2a squared minus 5ab plus minus 3b squared. Get rid of that plus, because plus or minus is a minus. Okay, so let's see how people fared, should we say? Yeah, so we've got the most popular minus 2a squared minus 3b squared. Yeah, so that's just that. So now what we're going to talk about is effectively doing the opposite. So instead of figuring out how we can expand a bracket, think about how we can create one. Okay, and this is a process called factorisation. And all it's doing is basically finding this thing called common factors, which is basically two numbers or things that can be multiplied together to give the same thing as you started with. Okay, so for instance, 10, okay, you can write 10 as 2 times 5. Okay, so factors of 10 are 2, 5. Okay, it also has the factors 1 and 10, so you could write 10 as 1 times 10, which would be a colossal waste of time, but it is nonetheless a factor. Okay, and this is really important. So this is used quite a lot to help solve equations in all aspects of what you'll be doing for the rest of your degree. So examples, yeah. So we've got an expression here, 3x plus 12. Okay, so if we can find a number or set of numbers that can be multiplied up to give 3x and can be multiplied up to get to 12x, if those are the same between those, okay, then we can make a bracket with that. Okay, so you can write 3x as 3 times x. Okay, so the factors of 3x are 3 and x, and multiplying those two go together. And 12 has a bunch of factors, so it has 1 and 12. You can add those together. Sorry, times those together and get 12. You can get 2 and 6. You can times 2 and 6 together. Those are factors of 12. But you can also get 3 and 4. Okay, so 3 times 4 is 12. So that means that the number 3 is a common factor to both parts of this expression. Okay, so that means we can take 3 out and put the rest in brackets. Okay, so we can, instead of 3x plus 12, that's an x, not an alpha, we could write that as 3 times x plus 4. They're the same. Okay, so this seems pointless now, but it is really important in terms of simplifying an equation if you're trying to isolate certain variables. Okay, so it's really useful. Okay, so in the one below here we've got x plus 2xy plus 3xyz. Okay, so that's, if we wanted to find the value x, if x was if this was an equation that calculated the density of the continental crust or the concentration of some kind of spawning algae in a stream or something abstract, but you can see for all of these things, so x is a factor of itself, so x times 1 is x. X is also in this and is also in that, so we could rewrite that as, so we've got x plus 2xy plus, what was it, 3xyz. So the common factor here is x. So this is x times 1. Okay? This is x times 2y. This is x times 3yz. Okay, so those are the common factors. X is one of those. So we can then take x out and have x times 1 plus 2y plus 3yz. Okay? So what we've done here is we've got this really complicated equation. If we wanted to work out what x was, okay, rearrange this equation to get x, it would be quite difficult because there are lots of different x's in it. Okay? But by factorising it and kind of moving this out onto one side, or basically into this bracket, that allows us to be able to rearrange that equation later on to us as to find the answer for x. Okay? That's harder. So what are the common factors in this one? What are the common factors? So just before, so we'll just do a quick, what are the common factors? So don't work it out, just what are the things that you're going to put outside the bracket? Word answer. So what are the common thing there? Okay, so this process of factorisation is really useful for this thing called solving actually quadratic equations. Okay, so there's this kind of linear equation which would be kind of y equals ax plus b. So that's the equation of a straight line. And then a quadratic equation is something like has got two x's in, where one is raised to the power 2. Okay, and there are other ones of these. So there's a cubic equation, which is an equation that's got an x cubed plus x squared plus x to the 1, and you can think of this as x to the 0. Okay, so they're generally named after the highest exponent, and there are lots of them. So actually, what I'm going to do now is just come out. Okay, so these kind of equations are really important in all kinds of areas of science. Okay, so these are kind of equations where you have variables and like basically x or y raised to the power of 2. Okay, so that this equation here is effectively a quadratic equation, and that is the equation that describes an ellipse. So it's used to basically in working out the orbits of planets around other planets of the sun. If you're doing anything with an equation of motion, so if you're moving something from one place to another place, okay, you're going to have to accelerate it, and this is an equation that shows you that displacement of that object, okay, as a function of the acceleration, the initial speed, u, the acceleration, and time, okay, and you can see here that this is as before we were talking about x and x squared. This has got t in it, so t is x in this case. Okay, so this is important if you're building a climate model and you're moving bits of the atmosphere or bits of the ocean around. Okay, you're constantly solving this quadratic equation. Okay, there's somebody else actually decelerating, which would be a negative acceleration. Okay. So another place these things crop up is this idea of these golden rectangles, or this golden ratio. So it's basically one way of defining it is a rectangle where one side length is 1, any unit, could be whatever, and the other side length is x. Okay, and the ratio of 1 to x is such that if you were to make another rectangle in this square. In this rectangle, sorry. So basically, if you were to put a square, maybe the next thing you will help. If you were to put a square in here, which was the side length of the short length of the rectangle, that would leave you a little rectangle at the other end. And in this case, the width of that would be 1 minus x. Okay, you see how that's 1 minus x? Okay, and depending on how long or thin your rectangle was, this would be variably a kind of a tiny little strip or a great wide big thing. Okay, but if x and 1 are at this golden ratio, the ratio of 1 over x is the same as x over 1 plus x. So no matter how many times you put a little square in this rectangle, the rectangle that you end up with will always be the same shape. Okay? And it turns out that this is a particularly kind of important ratio for a whole bunch of things. Okay? So basically, this equation, okay, here, so when 1 over x is equal to x over 1 plus x, means that the rectangle obeys this rule that whenever you put a square in it, the rectangle that's left over is always the same shape. Different size, but same shape. Okay? That equation describes that rule. And it turns out that then, this 1 over x is a specific number. Okay? And you can actually work out what that number is just by rearranging this equation, okay, and then solving the quadratic equation. So it doesn't look like a quadratic equation, right? It doesn't quite look right in that there's no x to the power of something. Okay? But what you do have here is two x's, we've got three x's, where they are two different powers. So the x at the top here, okay, that is x to the power of 1, yeah? Whereas this one is x to the power of minus 1. Okay? So you could do some rearranging of that formula to try and simplify it, and you would end up with an equation that has got an x squared in it. Let's just go through that, just because of, just because we can. Let's go over here. Can you guys see over here? So we start out with an equation that's 1 over x, and that is equal to x over 1 plus x. Okay? So if I'm going to rearrange that, if I'm going to do some mathematical manipulation, my one rule is I can do anything I want as long as I do it to both sides. Okay? So the first thing I'm going to do is I'm trying to get, so I can write this as basically, I could write this as, that's equal to x to the minus 1. Okay? So I want to get rid of x to the power of minus 1. Okay? So what I'm going to do is I'm going to times both sides of this equation by x. Okay? So this is going to be x times 1 over x, and that's going to be times x. Yeah? Happy campers? Which is, I guess, the same as x divided by 1. Okay? So this then becomes x over x. Yeah, 1 times x. Pretty simple. And this becomes x squared over 1 plus x. Okay? This is obviously now 1. Okay? Now I could move this over to one side if I wanted to. So I could go and get 1 plus x, okay, equals x squared. Now we're starting to get something that looks a little bit more like that quadratic equation. Okay? I could take this whole thing from both sides. So this would then be 1 plus x minus 1 plus x is 0. Yeah? Minus 1 minus x. Okay? So now I've got something that looks like a quadratic equation just from that simple rule. Now you can solve that, and there are a number of ways to solve that, but you end up getting x is this irrational number here, and this is really quite important. Well, also, yeah, so basically this is quite a pleasingly shaped rectangle, and artists figured this out.
It's supposed to be plus x.
Is it?
Yeah.
So I've taken the whole.
It should be 1 minus x.
Minus 1 plus x. Okay, so that's minus 1 times, and basically.
No, but it should be x squared plus x minus 1 as the overall equation.
Should it? I don't think it should.
It should. X squared plus x minus 1 equals 0.
Well, I've minused it from both sides. Textbooks have been wrong. So I have actually put the working of this on Learn. So I'm going to go through that later on and send you all a link to it. But I'm pretty sure that's right. That's wrong. Anyway. But anyway, so this ratio turns out to be quite pleasurable to look at. If you look at, if you draw these rectangles and kind of like draw semicircles within each of those squares, you get this kind of nice spiral, which appears in nature a lot. Also, if you look at the numbers of things on things that grow, so leaves on kind of around a stalk or little kernels in a flower thing, they tend to always occur in this thing called the Fibonacci sequence, which is basically the first number in the sequence plus the second number in the sequence equals the third number in the sequence. The fourth number is these two plus together. This number is the two numbers preceding it. Okay? And if you look at things in nature, they quite often have these numbers of things. So if you buy a pineapple and you look at how many spirals of like knobbly bits around the edge of a pineapple, it's one of those numbers.
Why?
I can explain why, but it's weird. So we might run out of time. Yeah. But anyway, if you look at the ratio of two Fibonacci numbers, the bigger you get, the closer you get to this magic ratio. Okay? So I'm going to stop there. Does anybody want to know why you get these ratios? Okay, so I'm going to stop recording because this is going to be...
No, take it away.